satellite is a smaller mass body which is orbiting continuously around a body of much larger mass. Moon is natural satellite of Earth. Earth is natural satellite of Sun. Jupiter has around 79 satellites, natural satellites. When we talk about satellites, we have primarily two kinds of satellites. One is natural satellites, the other is artificial satellites. When we say Moon, Moon is a natural satellite of Earth. We have artificial satellites. Artificial satellites, they are used to study the atmosphere of Earth. They are used for communication like telecommunication or for TV and radio signals. And they are used for spying also. These satellites, artificial satellites, what we talk about, they are on two planes they are generally orbiting. One is in the equatorial plane, that is above the equator, and the other is a plane which is perpendicular to this equatorial plane passing to the north-south pole. So if we say, if this is Earth, we say this is Earth, this is orbiting like this, so this makes equatorial plane. So one is the satellites, they may be orbiting like this, along the equator they may be orbiting. The second is this way. When we talk about the satellites which are moving this equatorial plane, they could be geostationary satellites or they could be satellites which are very close to the surface of Earth, let's say 200 kilometers or so. These geostationary satellites, they are always stationary with respect to Earth. These geostationary satellites, they are geostationary, that is stationary with respect to Earth. It means their angular velocity is same as the angular velocity of Earth. It means if the Earth takes 24 hours for one rotation, this planet, this satellite will also be moving along with this, and this will also take 24 hours to complete one revolution. While those satellites which are closer to the surface of Earth, let's say 200 kilometers or so, they are moving at a very faster speed and they may be completing many number of rounds in 24 hours. Their time to complete one revolution is almost 84-85 minutes or so. So in 84-85 minutes they complete one revolution and then they go for the next revolution and so on. So they complete number of revolutions in a day. Whereas geostationary satellite, it has a time period of 24 hours. That is the same time period which Earth takes to complete one revolution about its own axis. So when we say that is a man-made satellite, what is the basic principle of man-made satellite is, suppose we take this as Earth and there is a huge tower. This is a huge tower. From here, let's say a body is just projected with a small horizontal velocity, so it will fall like this. If we give a greater horizontal velocity, it will fall like this. It will still give a greater velocity, it will go like this. If we still give a greater velocity, it will go like this. And if we give a still greater velocity, it may start orbiting around this Earth. If we say this is Earth, it may start orbiting around the Earth without falling to Earth, and this velocity with which now it has been released so that it is continuously orbiting the Earth, that is called VO, that is orbital velocity. If you wish to understand that is how satellite is launched and put in the orbit, in simplistic manner, we can take it as there is a rocket or space shuttle which carries this satellite. It goes to this height, and over there, when it reaches over there, let's say this satellite with the rocket, it reaches over here, then the small rockets, they are fired so that it is aligned like this, and once again the rockets, they are fired and it starts orbiting in this circle of desired height. While doing the chapter on circular motion, we have dealt with number of cases like when the stone was tied to a string and it was moved in a circle, so the tension it was providing the central force. We had also understood that is if a body is moving in a circle, so this motion is circular motion, and for circular motion, when a body of mass m is moving with velocity or speed v in a circle of radius r, it demands a force that is called centripetal force, which is equal to mv square upon r. Now when satellite is moving around a planet, certainly this is also a case of circular motion. If this is a case of circular motion, then certainly once again the centripetal force will be required. This centripetal force is going to be provided, this requirement is going to be met by F is equal to gmm upon r square, that is force of gravitation between the satellite and Earth. So over here, if we take this as Earth, if we take this as Earth, from the center, this is satellite. Satellite is obviously a point mass body as compared to the dimensions of Earth. This is very small, so we can take it as point mass body. And let's say this is orbiting in this circle, and from here to here, let's take it as r. And it has a velocity v, mass is m. So obviously when it is moving in a circle, it has a requirement of mv square upon r. This requirement is going to be met by gmm upon r square, where capital M is the mass of Earth and small m is the mass of this satellite. M and m they get cancelled, so v square is equal to gm by r, or v comes out to be under root of gm upon r. So this is the orbital velocity that this satellite should be having so as to move in a circle of radius r around the earth. So this is r from the center. Now if we say from here to here is r, capital R, and from here to here is h, and this satellite is at a height h from the surface of earth, so it means from here to here the total r, so r is going to be equal to r plus h. So we put it over here. So orbital velocity comes out to be under root of gm upon r plus h. We also know a very important substitution, that is, if a body of mass small m is over here and this is earth, radius is capital R, mass is m, capital M of earth, this is earth. So earth is pulling it towards its center with a force that is mg, and that is equal to gmm upon r square. So from here m and m get cancelled and gm comes out to be equal to gr square. This substitution you will be using number of times. Over here gm is equal to gr square, so you can put it over here. So this comes out to be gr square upon r plus h. So this comes out to be r comes out g over r plus h. If h is very small as compared to r, if h is very small as compared to r, so this becomes equal to r only. So this comes out to be under root r g, and when you put the value of r, radius of earth, as 6400 kilometer, the radius of earth is 6400 kilometer, and g you take it as 9.81 meter per second square, then v orbital it comes out to be 7.9 kilometer per second. And when you put the values over here, let's say for this, when h is very small as compared to r, that is around say 200 kilometer or so. So this, the time period, if you put the values, that is total circumference, that is the total circumference over velocity, that is 2 pi r by velocity of orbital, when you put it, it comes out to be almost around say 84.6 minutes. That is, the satellite completes one revolution in 84.6 minutes around the earth. So we see that is orbital velocity is independent of the mass of this satellite and depends upon the mass of this planet and the radius, that is at what height it is orbiting around the planet.